So the next overall theme of this that you actually see in the back of the chapter for the Rosen book is a well-ordered principle and least element. It's in back of the book and it's not very large, but I still want to go over it because of two things that really come in this. Is that every non-empty set of non-negative integers has a least element. And I'm going to show you an example of that here in a moment, so bear with me. But it sounds exactly like it means that the lowest value from within a set, the set can be explicit or from a function. It's important since the last element is used in mathematical induction, or least, I said last, so the least most. Notice it was P of 1 was our base case, or P of 2. It's really, really low compared to P of 1,000, unless we are strictly told by the range of the value in that proof. We'll always try to get the least value in there. So going back over least values in an equation, if we're given positive integers, again with that plus there, so be careful with that, that's going to be 1. But if I was given all integers, including 0, that would be a range from negative infinity to, frankly, it doesn't matter what positive infinity is because I'm looking for the least. I would not be able to get an answer from that, and that would be really difficult for a proof. We'd have to try something else. If we had n is, that should be an element within C plus, and again, notice we're given the range. We had a couple of times where we're given a certain range of that, then it's going to be our 3. Here's a prime set, we just picked the lowest number. A rational number, now a rational number is going to be a fraction. We can make that fraction even smaller by increasing Q, so it's no longer an integer anymore, and that's a problem. Notice this is a non-negative integer, so we couldn't even do that one. And then if it is a non-negative integer, 0 is actually considered a non-negative integer, so be careful. You don't see it too often in the examples I'm giving you here, but I'm waiting for the homework to go get you. So just a heads up on that. And let's go over an example here. Just give me a moment. Here's a well-ordered property in use. In the book, it doesn't actually explain a couple of things in its overall set, so I put Q as quotient, R as remainder. And that's going to help us really kind of understand, really, frankly, some of the lettering that we're using here. In a well-ordered property, you can read the rest of this, in a proof of a division algorithm, go figure, it states that if an A is an integer and B is a positive integer, we have to be careful about that, then there will be unique integers of Q and R, which is the quotient and the remainder, such that we have this equation where at all times R is going to be greater than 0, but B is going to be greater than R. So what I do here is I just show a couple of examples just to kind of prove this out. So here's my 13 divided by 2. I'm using the equation. I have my 13 here at the A part, the 2 at the 6 part, my quotient. I have to times this by 6 to get 12 and then add 1, notice it's an addition, in order to get my 13. So my A would be 13, my B is 2, my Q is 6, and my R is 1 out of this entire equation I'm pulling right here. Now, I did the same things with some other numbers. Matter of fact, I used a negative A just to kind of prove everything still works out. And the interesting part about this is that you'll notice, and you know about remainders already. They're already going to be less than the quotient, and that's basically what this is backing up here. So in all of these cases, it did come out that R is going to be is greater than 0, but is still going to be less than B. And that's because of the remainder or the division property that we have. But you and I, as programmers, know it as remainders. So that's how we can get the well-ordered property in a particular algorithm or particular proof for this, algorithm.